Hello everybody, this is Dr. Sergey Sargasov, and I want to talk about the number of factors of any number that you can possibly imagine. As far as positive integers, the natural numbers, right? So 1, 2, 3, 4, 5, and so on. So anyway, let me talk about a number of factors. We have to understand very importantly what are prime numbers. And we've done this quite a bit in our other lectures already, prime numbers. And what are composite numbers? So prime number, let me write that, is a number that only has two factors. One, which one divides anything, and itself. So basically it cannot be divided by any other number, right? Like 5. 5 is just 1 divides 5, 5 divides 5, right? There's no 2, 3, 4, nothing will divide it. And as we're doing the number of factors idea today, topic, and we'll talk about some other little mini topics on the side. So prime number, no factors aside from 1 and itself, okay? It's just definition, all right? Now what is a composite? If it's not prime, composite number. So if it's not prime and it's not a 1, okay? Hear me out. 1 is considered to be neither prime nor composite. So remember, note that 1, number 1, the number, let me just write that, the number now. The more writing sometimes is better, not worse, is neither, okay? So that's just kind of on the side, it's a definition, basically we have that, and there's a reason for it, okay? But so prime number, no factors aside from itself and 1, composite number, at least one factor, at least one factor other than, in addition. Okay, so to the 1, and itself. So let's say like C, call it C1 and C, which is P. Okay, so we'll have P is itself a prime. So P for prime, C for composite, and of course 1 for just a 1. But anyway, so let me talk about this, all right? First, prime numbers and factors, and let's say somebody asks you, factor the number 12, okay? So, okay, we're like, I call it the prime factor tree. A lot of people call it that. And so I asked myself, you know what? Let's do the work in red. All right, so, for example, I know 12 is easily 2 times 6, right? Now, you could have said 3 times 4. Let me do that. Let me say, it's 3 times 4, right? That's also true. And again, 2 times 6, it will give you the same result, ultimately. So 3, all right, what about 3? 1 and 3, like I can't divide it. And you think about it, what you're really doing is you're testing 1, 2, 3. And no, of course, no number bigger than that will work. So we just ran numbers from 1 to 3, only 1 and 3 divided, right, 2 doesn't. And so I'm going to circle it, it's a prime number. Now 4, okay, 1, well, obviously, but so you start with 2, right? So 2 divides it, and it's not a 4. All right, 2 times what? 2 times 2. And then, of course, 2 and 2 are both prime numbers. And so we can say, remember, by the way, if it's 2 times 2, we say that's 2 squared, right? So this is equal to 2 times 2, 2 squared, times a 3, right? Okay? And so those are that's the prime factorization, okay? Prime factorization of the number 12. This is called the prime factor tree, okay, right here. So that was what we did there, all that. This is prime factorization. And but what about the factors themselves? All right, so first we're like, you know what, we're going to try numbers that just divide it. All right, 1 divides it. Now 1 divides it and it gives you what? 12, right? So I'm going to put 12 on the right. Okay, what else? Well, 2, we know 2 divides it. 2 times what? 6, right? All right, 3, yeah, 4, right? And so these are the factors, okay? The factors are, and let me do this. Let me say, you know what? 3 times 4, 2 times 6, 1 times 12. And you may wonder, what about, why are we stopping at 3? Why not go to 4? Oh, we've done 4. And so that's the idea. So, we're not going to, why go further? If we have a 5, we have something less than 3. We already checked everything 1, 2, 3. So think about it. Here's an idea that I want you to tell you. If you have, oops, there's a, let me do that. If you have a number, right, any number, and you want to know, what factors do I even check, okay? Let me say this. You will, to test numbers, factors, let's say numbers, to find factors. All right, let me say, one way to do it, let me say this. So, to find factors, okay, you actually want to find the exact factors, right? One way to do it, without any prime factorization, because that's really stronger of an idea, okay? That's what we did above there, right? Factorization. But we didn't do it yet. I just was starting with prime factorization, just telling you what it is, okay? But to find factors, try 1, 2, then 3, 4, 5, and so on, all the way to number closest but smaller, closest to, let me say, number smaller, okay? You'll see what I'm doing here in a bit. Smaller and closest. Let me write that and here instead, right? So I'm going to move this around. Let me move this a little bit here and right here. Okay? And closest to, guess what? It's kind of something somebody was surprised here, to the square root of that number, n. To find factors of n, okay, try 2, 3, 4, 5, all the way to the number closest to, less than. You don't have to go over, because if you go over, there's a number less than, right? So think about it. Square root of 12 is 3 point something, right? It's 12 is bigger than 9, it's less than 16. And so we can go 1, 2, 3, and we're done. Because if you have a number bigger than the 3, whatever, you square it, you're going to get bigger than 12. Because it's the square root of 12, right? So let me show you kind of something that has a square root. For example, let's do kind of like something kind of a little bit more involved. 6 squared, right? So because the 6 has a 2, a 3, right? Try 6 squared. So n equals 36, all right? So factors, right? We're like 1, 36. Let me do this in red, right? So factor, n equals 36. Let's do that, just a little example here. So, all right, watch this. Let me show you where I'm going with this. So we can do, all right, 1, and then of course times 36. That's easy. Okay, what about 2? Yeah, 2, 18, right? We can divide 36 by 18. What about 3? Oh, 3, 12, right? Okay, that's good. 4, yeah, 4 times 9. A lot of this stuff is working, all right? What about 5? No. What about 6? Yeah, 6. Oh, 6 is just times 6, right? And then 4 times 9, 12. And so you're wondering, okay, well, how did I know that, square root of 36 is 6, and we don't go after 6? Again, if I try 7, that would have been a number less than. We don't have that. We're with 7. 8, 9. Oh, 9 already we did. You see, so we don't have to do it again. So that's the idea. Closest to, smaller, or equal to, less than or equal to. Look, obviously we did 6 is equal to, right? Smaller, or, no, let me just say less than. It's actually mathematically be more like this. Number less than or equal to and closest to the square root of n, okay? Obviously, it can be the square root of n. So that's the idea, all right? And so let's do another example, just in real time to kind of show you that part. That's kind of important. So factor number, let's do something a little bit more involved. For example, 108, all right? And 108, okay. So we know, all right, the square root of 108 it's bigger than 10, right? So, and it's less than 11, because 11, think about it, 10 squared, like square everything. 100 is less than 108. If you square everything, it's less than 121, right? So obviously that's working, right? So if we're with 10 point something, so square root of 108 is approximately 10 point da 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 da, right? Like it's something, I don't know, right? But that means that less than this is just 10, right? The closest to it. So that means we don't have to try numbers outside of 1 through 10. Okay, so here we go, 108, for sure 1. And there may be a lot of factors, but let's see, 1 times 108, okay? 2, yeah, 2 times 54. 3, let's do the commas, okay? 3, yeah, 3 times 36, okay, that's kind of made of 36 anyway, right? 4, yeah, 4 times 27, right? 5, nope, no 5 in it. You can check, there's like no 0 or 5 at the end, right? Digits, and there are unit digits tricks as well. Okay, 6, that's going to be 18, right? And we're almost done. 7 doesn't work. What about 8? Yeah, actually, no, 8 doesn't work. 9, what about 9? 9, 12, oh, and we're done. And so that is, how many factors? Number of factors? Number of factors, actually, that's what we're going to, kind of the beginning of the topic itself. The name of this class, lecture, or whatever, is the number of factors. So let's just check it out. 1, 2, 3, 4, 5. We have 6 on the left, 6 on the right. Oh, 12. Let me do this in a different color. Let me not do that quotation mark, because it seems like almost a factorial, if you know what that is. So let's just, the exclamation mark. So number of factors, 12. Let's go around and mess around with factors. What about number of factors here? That was 1, 2, 3, 4, 9, right? Number of factors here, 9. All right, okay. What about this one? Oh, number of factors was 6. How do we do this? How do we find number of factors without doing too much? All right, here goes. It's basically the fundamental theorem of algebra. Arithmetic. It's really cool. Fundamental, and it's like a different version of it, but the different versions of it a little bit, but fundamental theorem of arithmetic, okay? It's basically my take on it, okay? If you talk about fundamental theorem, there's basically 3. There's fundamental theorem of arithmetic, like, numbers and operations, fundamental theorem of algebra, and fundamental theorem of calculus, all right? And I'll tell you all of those just kind of briefly, just for fun, all right? Just, there's nothing too impossible about it. Calculus, if you know a little bit of calculus, it's basically saying that if you take the area under the curve, like you have a graph and that's the same thing as the integration, okay, of that function from kind of left to right, from the endpoints, like from A to B, if you have the area structured between A and B. And I just want to say that also the integral is the antiderivative. You invert, basically taking the derivative. So for example, if x cubed goes to 3x squared, 3x squared, integral of it would be x cubed. So how about what's the integral of x squared? Well, it's 1/3 x cubed, plus a constant if you do indefinite. But that's the idea. And so that combination, that connection between area, integral, and the antiderivative is all basically that fundamental theorem of calculus. And it runs deeper, of course, than just me saying a few lines and a few sentences. Now, what about fundamental theorem of algebra? Well, to me, some people kind of say it a little differently, and they say this is a corollary to it, but I would basically say this, okay? It's when every polynomial, let's say like x to the 10th, plus 7x to the 9th minus 3x to the 7th, blah, 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 like some polynomial with a bunch of integers and even, random numbers, real numbers for coefficients and powers of x. If you start with a power of x, like x to the 10th, you will have some kind of 10 factors. It doesn't have to be nice ones that have rational zeros, okay? It could be x plus the square root of 3 times x minus 2 minus 5i, okay? It could be a lot of different weird things, but it could be 3x minus 2 if you had a coefficient other than 1, like on the x to the 10th. But you will have x to the 10th, you'll have 10 factors. They can repeat a little bit. It's called multiplicity. So it seems like less, but they can repeat. But you have, not necessarily different, but you have 10 factors. They don't have to be distinct, okay? Because you can have like x minus 3 squared, right? So there's 2 of them, so that counts as 2, not 1. That's the idea. Fundamental theorem of algebra, again, if you have an x to the 17th, you will have some kind of 17 factors. So some kind of 17 zeros. Yes, it could repeat, then you have kind of less different ones, but that's the idea. All right, fundamental theorem of arithmetic is talking about prime factorization. It's like zeros, polynomial, you can factor it a lot. fundamental theorem about arithmetic. A number, okay, we're talking about numbers, there's no x, right? Number, you can factor it a lot, basically into unique, this only one type of prime factorization. What I talked about right here, you see prime factorization? This is the unique prime factorization of 12. Yeah, it's a 2, and a 3. I mean, let's go order of smaller to larger. Let's not do, like, I don't want to do this, okay? So that's the idea. So I'll just go in the order 2, 3, right? 2 times 2 times 3. It's okay, 2 squared times 3. It's not 2 cubed times 3. It's not 2 times 3 squared. It's exactly the only possible and unique, and exactly it has to be something, and that's its possibility of doing it, is the fundamental theorem of arithmetic says basically that, hey, you know what? We have a unique prime factorization for every number. Now, it seems kind of like common sense. Yeah, of course, if I have like 2 squared times 3, it's some kind of specific number. But it's not that easy. You know, everything has, sometimes the easiest or seemingly the things that most make sense, like common sense, actually are the deepest, the hardest to prove, and the hardest to realize in mathematics. And there are a lot of like contrary, seemingly true, but not ideas. So, and I'll keep it there. But anyway, so look, I'm going to say it this way. This is again my take on it. Some people say this is like a little bit continuation of that theorem. Some people say it's a little bit before that. But every number has unique, so that's very important. It's one and only. You can't do like 2 squared times 3 and 2 cubed times 5. Like it's only one thing. 2 squared times 3 for 12. Unique prime factorization. Okay, factorization. So that's important because then we know when we get the answer, whatever, we're done. Like there's not another, right, and so on. So, okay, now let's find number of prime factors. Let me show you. Now we're going to do number of prime factors. So not number of prime factors, number of factors. So what you do, okay, equals, ready? Like what? Like how do you find it? Let's get that. Let's first practice a little example. We've done above. So, for example, let's do 12. Okay, we know there are 6 factors, remember? 6 factors. So 12 is equal to 2 squared times 3. We already did that above, so I'm just copying it. Okay, now look. Factors of 12. Well, we know, let me write them this way. 1, 2, 3, 6, 4, 6, and 12, right? Those are the numbers we just had. I'm just going to write them again. And let me lower it just a little bit so we can have some space. So what happens is this, look. 1 is what? It's everything actually is a power, if you think about it. Everything, okay? I'll just write them again later, okay? So 1 is a power of 2. How many 2s? There's no 2s. 2 to the, by the way, anything to the 0th power is a 1, everybody. I've mentioned in another lecture quite a bit. Like, this is a quick gist on why you always define it to be, let me share on the side. I know people can forget this. So look, y is a to the 0th, a is not 0 though, equals to 1. Why? Well, because if you do, let's say, like, just kind of let's do some one thing, like one basic thing. Let's do a squared times a to the negative 2, just something, okay? We can do a to the 1, negative 1, right? This means exactly, first of all, you add the power, so that's a to the 0th, right? 2 negative 2. But also, that's a squared times 1 over a squared, and that's a 1. So you see this is going to be a 1. Just an idea that that's one idea. And of course, you could also do like, 1 over a squared, then 1 over a, and then that's a to the 0th, which we don't know what that is, maybe. And this is a what? Then it's a times a squared, da da da. So basically, look, you have to have this as equal to 1, because a times a, what times a is a? It's a 1 times a. What this times what gives you just a, what that times a over a. That's a 1. So that's the idea. Okay, so some different versions of it. Anyway, so that's a 1. That's why I did that right there, that orange. Okay, one way to do it. And then look, well, I mean, sorry, this is going to be a 1. Anything to the 0th is a 1. Okay, now, anyway, times, well, how many 3s? Also 0. It's just a 1, right? How about 2? 2 is a factor of 12, and it's actually 2 to the 1 and no 3s, right? Okay, 3 has 1 3 in it, right? So no 2s, 1 3. Let's see if you can follow. 4. What's 4? Well, 4 has 2 2s. That's 2 squared, but no 3s, right? What about the 6? That's 1 2 and 1 3. And what about the 12? That's the everything, the 2 2s and the 1 3. So notice, every factor is a power of 2 and a power of 3, the product of those, right? And you can't have more than 2 2s. You can't have more than, guess what? You can't have more than 1, 3, right? So number factors. So you basically, let me say this. So you can have, so each factor is some kind of product of powers of 2, right? But up to 2 of them, right? Up to 2. And powers of 3. Of 3 up to 1. In other words, we have, so we have 2 to the A times 3 to the B, with A in the set. Let me do the element of. That means element of. Let me make a nice little element of symbol. A can be 0, 1, or 2. B can be in 0 to 1, right? Because it can be nothing, or it can be that 1, 1, 3. And this could be 0, 3s, 1, 3, 0, 2s, 1, 2, or 2, 2s, right? And so what happens is you're like, you know what? There are 3 here possibilities. There are 2 possibilities here. So you're either 0, 1, 2 there. You like, let's say you select this one and that one. Oh, that's a 2 and a 3. You select this one and that one. That means there's 2 2s, so 2 times 2, and no 3s. And you select 1 from the 3, 1 from the 2, and you know how that combinatorics works, right? I've mentioned that a lot. You would do times, right? And you would get 6 factors. And then we know there are 6 factors, okay? So let me do the 2 other examples, the 36, 108, and basically I think you'll have it from there. So let's do this. Factors of number factors of, let's do n is equal to 36. Now we know, I think there were 9 of them, right? All right. So 36 is equal to, remember we did this, it's a what? There's a 4 times a 9, so ultimately you get 2 squared times 3 squared. Okay, everyone? You can try that. 2 times 2, and then 3 times 3. You can do the prime factorization tree, okay? And so anyway, what happens? Well, A is equal to 2, right? There are 2 2's in there. B is equal to 2 also, 2 3's. And you can have that set 0, 1, 2. Don't forget there's a 0. Huh? The set 0, 1, 2 again. And you take 3 from there, and you get 9 factors. And we had 9 factors, so remember we did that. I wrote it up there, 9 factors. Okay. Now, what did I do? So how do I do a formula? The formula is, if you do A plus 1, you see this? This is 2 plus 1 right here. Let me kind of do this a little bit differently. So I'll say, you know what? You have that 0, right? So it's not only 1 and 2, because that's 2, but also add a 1, because there's also a 0 possible. 2 plus 1, that's the 3. This is also 2 plus 1. Basically, A plus 1, B plus 1. So let's do another, and then we'll do one final example. So this one, let me show you. Number factors of 108, which was what? Let me do this in the right color. 108 was, it's 36 times a 3, so we have extra 3. So it's 2 squared times 3 cubed, okay, everyone? Yeah, that's what it is, right? You can check it out. 4 times 27, right? And so what we do is we say, you know what? The number factors, okay, A is a 2, right? And you have numbers 0, 1, 2. B is a 3, powers 3 there, okay? 0, 1, 2, 3. And you see there's 3 here and 4 there, because A plus 1 is actually 3. B plus 1, that's why, you know, that's because we have 4 possibilities. This one, that one. And then we have 3 times 4 is 12, and we had 12 factors. Okay, so this is only when we have two different, and we checked there was 12 factors, 2 different prime factors, 2 and 3 possibilities, right? What if I had a different one? So here, finally, let's do one more, or at least one more example. So what about number factors of the number, let's do this. Let me show you something really crazy cool. Let's do a number like 2,880,000. Yeah, why not? Like, yeah, I know this number has a lot of factors. I sometimes use a specific number in my classes, so let me show you. Now this is, you know, seemingly more intense. All right, prime factorization, everyone. Let's do this. First of all, we can see there are 4 10s in here. Every 0 accounts for a 10, right? 10 times 10, so you add a 0 and you multiply by 10. So let's do this. Let's say, you know what? This is a 10 making this 10. This is also another 10, and this is going to give me another 10. This is going to be another 10. And we have a 288 left, right? Now, what is 288? Let's keep it easy. Let's say, you know what? It's a 2 times a 144. 2 is a prime number. Every time we get a prime number, we can't do anything with it. We're circling it. 10 is a 2 times a 5. Circle those. They're primes. 2 times a 5. Circle those. Primes. 2 times a 5. Right? Circle those. Primes. You can't do anything with 2. You can't do anything with 5. 10 is a composite. 2 and 5 are primes. 144, different ways to do it. 2 times 72. 3 times 48. You know what I'm going to do? 12 times 12. Okay? 12 is, okay, 2 times 6. Or maybe you thought 4 times 3. Okay, 2 times 6. 6 is a 2 and 3. 4 is a 2 and 2. You still get 2, 2, 3. 2, 2, 3. 2, 2, 3. Okay? All right. So 2,880,000 is actually equal to, it has not only 2's and 3's, it has 5's. So let's check it out. 2 to the 1. Let me kind of do this. That one. 2, 3, 4, 5, 6, 7, 8, 9. We have 2 to the 9th power times 3. How many 3's do we have? 1, 2, 2 3's. 3 squared. How many 5's do we have? 1, 2, 3, 4. 5 to the 4th. And so guess what number of factors you would have? Every factor, each factor is 2 to the some power a times 3 to the some power b times 5 to the some power c. And when you have those powers, you add 1 to each of those powers and multiply, and you get the number of factors. Because a is in the set 0 to 9, right? So you have actually 10 numbers because you also have the 0. B is in the set, what? 0 to 1, 0, 1, 2, right? Because it's just 2 is the maximum of 3's you can have. So you can have no 2's, 1, 2, or 3 2's. And C is in 0, 1, 2, 3, 4, okay? So we have a plus 1 is a 10. Get it? Number of factors of possible, just for how many possible 2's do you have? 0 through 9, that's, so you take that power, add a 1 to it. Take this power, add a 1 to it. And that's going to be 3 possibilities here. And C plus 1 is going to be, you can see, 5. So number of factors is equal to 10 times 3 times 5. And that's not difficult for us to multiply and get 15 times 5. 10 is a 150, which we do not want to write those out and guess them at this point, right? Wow, cool, right? All right, that's the idea, everyone. And so I hope you enjoy this session and have an amazing rest of the day or evening. And hopefully we'll do another one soon. All right, bye.